recording?
Oh.
Yeah, we're recording.
Awesome.
Yeah, a little card.
All right, cool. Well, thank you guys for coming out. We came down to San Diego as part of the Carbon Robotics Accelerator, and so for the last few months, I've been excited to come and speak to you guys because we keep hearing about this club that we've got to go see. So we are Carbon Robotics. This is Dan. I'm Rosanna. We are the co-founders. This summer we grew to a team of 8, so we're a little bit bigger now. But basically, we build a robotic arm. This is a version of it called KATIA, stands for Kick-Ass Trainable Intelligent Arm, and it has the capabilities of an industrial robot, a 1 kilogram payload, 1 meter work envelope, and sub-millimeter precision. And it has the capabilities of an industrial robot. Will have the price of a laptop. On top of the arm itself, we're building a platform that makes it really easy for developers to interact with the arm. And I think our broader vision is that robotics development should be as easy as building apps for phones. It should be that you don't need to have a mechatronics background. You don't need to have to build your own robot in order to work in robotics. That's been one of the biggest problems up until now, has been that you need a lot of money because it's expensive and it's hard. And I'm sure as a lot of you know, you try and build a robotic arm, it doesn't necessarily come out the way that you wanted it to. And so by standardizing that and making it so that you can focus on what goes on the end, you can focus on the attachment point here, which is modular and interchangeable, and by the code to make it run, you can have these really cool robotic applications without having to actually build the robot yourself, because that's a waste of time, right? You don't want to have to build a robot every time you want a robotic application. And that is our broader vision of what we see the future of robotics. So this version of KATIA is what we showed at the demo day. We broke a few things, so we wanted to show it functioning, but in the rush for demo day, a few things snapped. But if you guys are interested, we'd love to walk you through kind of the evolution of the design and why we chose to do things in the way that we did and how it works. We've spent 6 of the last 12 months in Shenzhen, China. So a lot of the ways we were able to get the cost down was by visiting factories, because there are a lot of parameters that you don't realize that you can change to customize, say, Moses, for instance, until you actually go into the factories. And so we can talk about that, and we can also talk about some of the challenges that we've faced in hardware, specifically building here, I guess. And then we want to be more interactive, so Q&A, what you guys want to talk to, because I know Jeff is interested in a technology that we've invented a new sensor that turns the entire housing into a giant capacitive sensor. So we can talk a little about that if you're interested. So that is us. We've been in business now, I guess, 2 years almost, and we've got our first units will be going out to developers this year, early next year, and then we'll be doing a pre-order campaign as well. So we have a number of attachments that go on the end. We've done 3D printing, laser cutting, scanning, and recently decorated a cake, which was kind of cool. We have a little iPad app. You can actually, Dan, do you have your computer to show?
I can show the video.
Yeah. So we made this app where you sketch out a design on the app, and then we handle all of the converting, the inverse kinematics of that and the G code and everything, so that all you have to do is paint your picture on app, press print, and then we had an extruder on the end that was actually printing it, which was kind of cool. Do you want to talk about?
We also make a gripper.
We also make a gripper. Yeah, but everyone knows robotic arms and grippers.
So just kind of going back to the beginning for us. The first arm we made was an industrial arm. It had a 12-foot work envelope, 10-pound payload, and we built this in a 15-foot room in San Francisco. So when you're tuning controls for something that can hit you anywhere in the room except for the corners, you start to really check your math. We went to China with the intention of building that, and we built another. We changed our design entirely because the supply chain there is different. And one of the big decision points for us was deciding whether or not to go to China. We have this very first version using like hand Dicom layout fluid and scribes and bridge ports, and then getting things a bit more automated and refining the design here and there. But we met a friend who had been doing manufacturing in China and was wondering, like, we know we're going to have to go to China at some point. Why should we go now when there's plenty of other opportunities? And he said to me, this was Will Hart from Spark, and he said that it was the supply chain in China is different from the supply chain in the US. And when you build a product in the US and then move to China, you're going to have to rebuild it for the parts that are there. It helps a lot to be building your prototype using the parts you're going to use for production, because every single parameter of every single part we test, and it changes and it affects the performance of our entire system. So that was now we've since learned you don't necessarily need to be in China to use Chinese parts, but do design with with production in mind, because it'll make a lot of things a lot easier down the road. But I want to talk a bit about the core drivers and the motors that we have been using, because that's probably been our biggest evolution. We started off with steppers, because they are the easiest, and you can do position control with the stepper using switches in your hands. You can generate those pulse trains if you know what you're doing. There's no speed to it. They're fantastic for position control. They're fantastic for gantries. They are really, really simple to drive. They are also incredibly inefficient in terms of the amount of power they're using for the torque they generate, and in terms of how much torque they can control and they can hold through their entire speed range. And in addition to just generating a ton of heat, they're also heavy as hell. And one of the ways that we're able to do things a lot less expensively is by putting all the motors and all the weight we can in the base, and having and minimizing our inertia as the arm goes up. We have an entire a power budget for as you get further and further away from the base, each gram costs us more and more in terms of components, in terms of our controllers, in terms of every single part of our bill of materials gets more expensive for every gram that's further away from the base. And when you have an industrial arm that has a 30-pound stepper on the elbow or on the wrist, you need 100, 200 pounds of motor just to move that stepper. And by eliminating that with our first arm, and by using a lot of belt drives and other things to transfer motion or transfer power from the motors in the base to the elbow and to the wrist, we were able to cut the cost of industrial arm down really, really far. But we were still using steppers, and they made our controls easier. They were kind of, but we quickly started to run into problems with that when we started doing more non-conventional photographic uses and things like that. When we were because we were really interested in use cases for arms and for robots that were not traditional robotics applications, because in some ways the bigger markets, the people who are assembling cars with robotic arms, they've already bought the robotic arms. They're not in the market for more. We were really, really excited by things like Bot and Dolly and by Gravity, which were shot by 3 KUKA robots, all carrying cameras, and suddenly they were able to do things with cinematography that had never been done before, because they could add automation, they could add robotic precision. And that was holy crap, this is a whole new this is a new game for an old industry, and that was really, really cool to us. And steppers they just would not give us the smoothness we needed for that. And if we microstep them down to get them to move smooth enough, suddenly we're dealing with we have no torque. So our very, very first one was steppers. Then we used BLDCs, and an industrial BLDC is our smallest motor weighs more than our whole arm now. It was just these massive things that would then need a massive gearbox to get it down to speeds which are usable. And on top of that, it was very important for us that all these things that we build are backdrivable and are trainable and are safe to work next to people. Because one big thing is with industrial arms now, they're really, really, really dangerous. And this is one thing that we realized a lot when we were developing this 10-foot, 12-foot arm, is that if your controls aren't right, this thing is not going to stop when it hits you. It's going to go through you. And so having everything designed from the beginning to be able to stop when it hits a person, it's to be very, very, very responsive to touch and to the force it's applying to an object, changed a lot of our design parameters. So we moved away from steppers, we moved away from BLCCs, and actually back to a version of steppers, which are three-phase. And most steppers you know and love, they are all, they have two phases, and there can be a lot of separate coils, but that determines the relationship between, and the biggest change with a three-phase stepper is that it's a lot smoother when you're moving it. You don't get the same cogging torque and the tick, 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 tick as you're turning the motor. You also don't lose nearly as much torque when you are microstepping. And this was, at the time, they only existed in tiny versions for gimbal controls and things like that. We worked with a factory in Shenzhen, and they were able to rewind motors for us and give us three phases coming out of them. The controls were easy enough to develop on our own, and suddenly we're getting really smooth motion out of steppers. And since then, they've become a bit more ubiquitous. The manufacturer we work with is now selling them to a lot of people, including, have any of you used Tormach's or the Tormach CNC mill? It's kind of like the big hobby CNC mill, but they are switched entirely to three-phase steppers just for the amount of torque they retain while microstepping. Another really fun thing with steppers in general, like when you're dealing with a robotic arm, with a gantry holds itself up no matter what. It's not just going to crash. If you're not constantly putting power in, you're constantly fighting gravity, and it's just going to crumple. And if you are dealing with microstepping with a stepper and you set the microstepping constant too high and its torque suddenly drops a little bit below what it needs to complete a motion, it will be moving smoothly, and that's super embarrassing. Not to mention, like when you've got a camera on the end of it, and just an expensive mistake. So that was the other reason to move back again to brushless DCs. And brushless DCs they're great for their power density, but the biggest thing is their power output is limited by the amount of heat they can dissipate. If you, some of the, I think it's Masaman, or one of the Japanese robotics companies right now, is making these extremely high-powered, very small brushless DC motors, and they're used in joints for anthropomorphic robots. And the way they get so much power out of a tiny joint is by water cooling the damn thing all the time. And that way they can pump 10 amps through a motor the size of this and just constantly remove that excess heat. And it won't. The limit for brushless DC is when it melts. And for our application, there are a lot of, the torque profiles, they change dramatically. They are, our peak torque is enormous. The amount of torque that we need to stop something that has been moving at full speed, to suddenly stop it, we're working against gravity, we're working against momentum. It's an enormous amount more than we need, enormous amount of power more than we need for just positioning or just holding something or moving something. We still have to account for that all the time. And with a stepper, your stepper has to be able to deliver that full amount all the time. With brushless DC, we can size them to only need to account for the root mean square output or torque requirements of our entire motor. And that way, if we know we're going to spend less than 20% of our use cycles at our worst case scenarios of suddenly deaccelerating with our full load at full speed at full momentum, then the motor only it can handle those surge loads, and it doesn't have to suddenly, we don't need to have a motor that can handle the highest load all the time always, because we can just dissipate that as heat for a few seconds and then we're fine. But brushless DCs are not meant for position control. They're meant for speed control. And every single brushless DC that's on the market right now it's commutated by a trapezoidal waveform, and that's because the electronics there are simple. You can use transistors, and you have three like trapezoidal waves that are 120 degrees out of phase, and you can by changing the speed of those signals, you can control the speed of the rotor, and it's just on off on off on off. It's not too far removed from a stepper, and that makes it really easy to build cheap little drones and all the cheap little like very inexpensive flying vehicles we've seen lately, because all you need to drive them are 3 FETs and three pretty cheap FETs, but they deliver their peak torque or their peak power output at 4,000 RPM generally. And
torque start, right?
yes, and when we are looking for high torque at low speeds and we're looking for position control, that either means having an enormous gearbox or having a motor that's dramatically oversized. And that's what you'll get with something like a gimbal motor for a that's controlling like a pan tilt zoom gimbal. Like that will just be a motor that's much bigger than you ever need, but it's but all it has to do is keep something level, and that way it's moving at low speeds, but it doesn't run into the same problems because it's it's overspec'd for the task. We're in this conundrum where like motors are our biggest cost driver. We have a 5 degree of freedom arm. We need 5 motors. We need 5 drivers. We need 5 of everything. And while brushless DCs were a nice improvement, they were not. They weren't. We were having to do a ton of stuff to mitigate the fact that they weren't meant for this. That they were meant for speed control, or meant for driving propellers and car engines. That got us. So after a ton of research, we started designing some PMSMs, which are permanent magnet synchronous motors. Permanent magnet synchronous motors, which sounds like every single other motor because it is, because the nomenclature for motors is it's an absolute mess. It's mayhem. A permanent magnet, like a stepper, has a permanent magnet and it is synchronous and a motor. And then like when you are doing this, like trying to find this part that doesn't quite exist yet in another language, it becomes very difficult, and you're going into these meetings with like you go into these factories and you sit down with the head of the company. If you don't meet the head, you're no one to them, so don't work with that company. And you have a translator. The translator is not necessarily technically inclined, so it ends up a little charades contest with like you and this other CEO drawing diagrams and like acting out waveforms and magnetic vectors, and you make some friends, but you also eventually get some product. So we were able to make some of these PMSMs, and they are identical to brushless DCs, except instead of trapezoidal commutation, they use sinusoidal commutation, and that is fantastic for us because it allows us to drive it with sinusoidal waveforms, and by varying the electrical angle between the 3 sinusoidal waveforms, we can determine the magnetic vector inside the motor, and thereby determine the position of the motor, the position of the rotor exactly. With the best brushless DC, you'll still have steps, and steps are unacceptable to us. So this requires some really fancy electronics and a lot of processing and a lot of controls, but it results in very smooth motion and very high torque at very low speeds, and great control over our force output, while also having very fine positional control throughout our range of motion. That also means we don't have to gear it down as much. That also means it makes it a lot easier for us to make the entire robot backdrivable, to make everything, any sort of force that goes into the inputs here, reflected back to the drivers. And that way we can sense exactly when it touches something, when you're grabbing it, when it says something, how much force it takes to lift a thing, and then adjust our controls accordingly. And it turned out like a lot of that was just from working with these factories, and they give us design input based on what the machines can do and what modifications to their design process are a bit easier, and what things are really out of the question. But at the time that we did that, we weren't placing 100 orders. We weren't placing 1,000 orders. We were going to them essentially as hobbyists, and they worked with us, and it was pretty phenomenal. If you have an idea of something that like you think maybe it can be done, maybe talk to a factory, and they are very often willing to at least talk, because now, like the companies that we've worked with, they have developed new product lines from chatting with us, and like that's a very beneficial relationship for them as well. So that's, I think, largely the story of our motors. You can see a couple of the versions here. We have some of these. All of these things here have been wound for us by a couple different factories, and you can feel the different amounts of cog and torque and smoothness, and some of them also have ratings for like how much power they put out. So these are all PMSMs, and they're nice. I'm really proud of them. And yeah, I think that was largely just the motor stuff. Do you talk about the belt drive things?
I don't know. What do you guys? Are you interested in those design decisions? Do you have specific questions?
I had a question. It sounded like you were describing what they used to call a hysteresis synchronous motor.
Mm-hmm.
Sort of the same thing.
It is very similar, except we don't have to generate the magnetic field in the stator. Instead, that is so like with an AC motor or a hysteresis motor, you have to generate two opposing electric fields, and first of all, it's inefficient in terms of watts. You can get more power out of that, but the bigger problem is that there is slip between the two rotating fields, and you will generate the field that we use permanent magnets for our rotor, not our stator. And then the stator has a whole bunch of coils on it, and by adjusting the current going through and the frequency of current going through the different coils, we can control the rotor position. With the motor you were talking about, you have to also generate the electrical field on the inside of the stator and on the rotor. Sorry, I get them. But you run into a couple problems. One, you're back to commutating the power somehow, and often that's inductive, but you need to get, like, we do everything we can not to put power through anything that spins, because that means a slip ring, that means something that is going to fail eventually. A lot of our joints, so that the range of motion is limited by the housing very often, because there's plastic and that will crack into itself. But also, we didn't want to have full 360 motion, because that means that we have to put a slip ring in. And a slip ring is essentially like a circle that's conductive and springs, and that will eventually wear down. And over 10,000 uses, that's going to wear down really, really badly. So some of the newer ones use inductive transfer, but then you're losing heat there as well. And we're really lucky. A lot of our friends are making drones, and every milliamp they leak means less flight time. So we're on the ground, but at some point we want to go mobile, and we're trying to pay as much attention to our power budget as possible. But it's a very similar technology.
And the Japanese used to use them for capstan motors for tape drives.
Yeah. We pulled apart a whole bunch of capstans to make some of our because we moved to a tendon-driven system, and we had to. It was odd that there was kind of this lost art of capstans for a period of time.
You ever seen the slip rings that use mercury?
Yeah.
Since you're on the ground.
Yeah, you can't buy those in the States anymore. We actually, at some point, we were developing a clutch. We had to make a variable clutch for one of our larger robots, and we're going through all these suppliers, and we're looking at this. Found one like friction patent. Oh God, this is really cheap. It has incredibly really good friction characteristics, and it's really like fire retardant. And again, like, I can't believe how cheap it is. It's totally asbestos. Just went to a friend like, what does this mean? Asbestos. It's like, okay, it's no longer an option.
It sounds like a lot of your development went into your motor drive electronics, and going from your trapezoidal to a sine
That's
wave.
one part that we
Triphase?
talked about. We've I mean, our electronic stack started off as a we were using Xilinx Zinc FPGAs and loved the power we got from them. Loved the speed that we could run our control loops in. But we have since made this shift to trying to make ourselves a development platform, and nobody is going to be able to develop on an FPGA. Like maybe some of the people in this room, but we're trying to get this to an Arduino level of development, where somebody who has had no experience in electronics development, who can maybe code a website, can work with robotics. So we want to get to the point where if you can code with an Arduino, you can now make robotic applications. If you can write a web page, you can make robotic applications. And FPGAs were a big wall between us and that.
So what would happen if you ran your sine wave drive through a standard three-phase brushless motor? Would you increase its?
It would be lost. The advantages would be lost. It will still run. It will absolutely still run, but because the motor is not wound for that, the windiness of brushless DC are specifically made to accommodate cheaper drive electronics.
Right.
And so like we have to. So in addition to the sinusoidal stuff, there's a lot of other a lot of crap that we have to deal with, like specifically just draining the current out of the phases we're not using. Because when we spin the magnetic angle or the electrical angle and the magnetic angle of the rotor, in the coils we're not using anymore, there's still current there. There's still an inductive field, and we need to dissipate that really, really quick. So we are generating 6 synchronized sinusoids at the same time.
So you're actively reversing current through the coils to
Yes,
shut them down, or
Yep.
so that's why you're running so you're running a positive cycle and a negative one, the ones you're not using at the same time, and then controlling the angle between all 6 waves. Wow.
on 5 motors at the same time.
So the phase and all. Wow, that's incredible.
Yeah, it's
I can see where your electronics is.
This is one thing that we don't get into very often, but it's it's put a lot of years on all of us, and is one thing we're very
So
proud
what's
of.
the maximum kind of frequency you're running on all those?
I would
pretty
have
much?
to I'd have to check with our
Just roughly,
guy.
yeah.
I want to say 2200 kilohertz.
Okay,
That's
reasonable.
That was with and that was at our that we were limited there by and this is just pre-demo day stuff, by the inductance of our lines going to the encoders in the back of our motors, and like the processors could handle more, but we need to get the electronics further away, and we didn't have a differential signaling we were switching our communications to LVDS signals, but hadn't made that transition entirely, and the distance increased our inductance, and that decreased the control speeds, and it's just.
And just as a completely sort of different thing, what kind of static noise environment do you have out of like current and stuff like that from the motors and whatnot?
Well, that's another fun thing, but
Okay.
it's actually it's not too high. We don't have I haven't poked around the latest version of the Gauss meter, but our biggest like a lot of the noise we're able to isolate with ferrite beads, and just positioning things a bit farther, because while our while there's a lot going on very, very fast, the signal's falling off at the exponentially as we move farther and farther away from the noise sources. So that's been kind of the bigger strategy, is having a big old ground plane and then move everything beyond that. But to the point where our biggest source of noise, our limiting factor, has become cable runs.
So you're using like coaxial type cables to
We're
shield
moving
it?
to coaxial.
Okay, right.
It was just leading up to demo day, we were like half the lines were LVDS, half the lines were just didn't have time to shield them. But that's the next challenge.
When you were doing your research, did you come across a company called CompuServe? They have a motor, it just, the way you described it, what you guys did is exactly what, I heard that discussion with Comsert. And they had 25,000 steps per revolution.
Yeah, there are some.
Amazing.
Well, so one thing is we don't have any steps per revolution.
Yeah.
It's a completely analog interface. It's closer to like. Have you ever seen like a resolver?
Yeah,
It's like that in reverse.
Resolvers.
Just we're powering it rather than it's generating the signal. That's so by changing INV, the number of steps is limited by our ability to make sine waves, which right now is very very good. But there have been a couple different applications for this technology. We've seen it in a few higher end servos. Hudson is a company making some of these right now, and then the biggest rollout of this technology right now that we've seen has been for extruders for injection molding, because you can make this enormous annular motor which has a big core in the center for plastic to flow through, and you can have it have very fine control of where it is and a lot of torque at low speeds, and that's what you need for an extruder. So less maintenance, extremely high cost, and there's a whole bunch of German companies making these ones which are which I can step through, and they wouldn't work with us. So
Are you focusing on the small arm now?
yes,
Because you mentioned the 12-foot.
yes, we initially demoed the the big arm and the small arm, and there were tons of industrial users that wanted the bigger one, and a lot of people were excited about it. But the one people were saying like, I want to buy that. It was the smaller one, and it was hobbyists that were interested in this, and that was. We had been going in this direction of like, we don't want to be just a low-cost arm. We want to bring robotics to people that have never been able to use robots before, that that aren't sitting in this room, that are kids that are growing up right now, and are just playing with their first Arduino. We want the next generation and the really really hard problems that are left in robotics. They aren't mechanical. It's vision. It's controls. It's how do you figure out each pick. We've been in so many factories, and they will have robots all over the place, but you can't pick out a single part from a bag of parts. It's so hard. And the person who is going to solve each pick is not necessarily a roboticist. It's probably a CS kid. And we are trying to open up robotics applications like that to people who don't know how to make the full arm. We don't want to risk making a full arm because.
And you shouldn't have to, right?
Yeah.
Like it doesn't make sense for robotics development for you to have to build a robot in order to build a robotic application. Everyone loses.
And it's like if people had like, we talk about cell phones a lot in our pitching, and how the value from a phone is not the hardware. That's great, but it's the apps that make it incredible. And if every single app developer had to have an ECE degree, we would have no apps. And that's kind of where we are in robotics today, in our view, and where we're hoping to see robotics go in the next 20 years.
So how do these little tendons work on your arm there?
Very carefully.
What's that all about?
Actually, on the other side.
Whole bunch of capstans, like bigger drive capstans, and then smaller Arduino pulleys that they are routed through to keep constant tension regardless of the joint angle. Right now, this is just tied in place because we're pulling everything down and doing a rework. But the idea is that so these slots in the bottom are 4 motors about this size that have drive capstans and sensors in them. And then each one of those drives 2 tendons which are in opposition, so it's constantly in tension but controlled by the same capstan.
Like little winches that
Yeah,
go
a
back and
whole
forth.
bunch of little winches. And it's allowed us to do some crazy things with routing and with bend angles and get the power of a big motor in a very very tiny little area, very far from our base.
So all the tendons end up down
Every single tendon ends up in here.
in one of
So
those.
there's no motors. There's a ton of sensors on each joint, but all of the drive electronics are, and all the power is in the base. That also helps us stop from tipping over.
Do you consider selling your technology?
You mean licensing?
Whatever.
We're really excited about building a consumer product. I mean, I think like what gets us really excited, and I think one of the ways we've been able to recruit like phenomenal engineers is a lot of people want to see this. A lot of people want to see this happen, and I think that in robotics you see a lot of these different approaches, and a lot of times with robotics companies they're very incremental. They're very they're looking at trying to get like some incremental cost down for the same application, for the same customers, for the same use cases, and you don't see a lot of creativity of like, you know what, maybe the most creative people aren't the people who've been working with robots, like Dan was saying. And when we think we haven't seen people creating like very, very high end but low cost robots, and also thinking about building a community and building a platform that makes it really easy for people. So I think that combination of thinking about really, really good hardware, very, very easy to use software, and then letting people work together. So it's not just like one person building something in a silo, but it's like a community being able to build these really cool applications. The way to make robotics ubiquitous is to be thinking about it in that way. And that's why I think we're so excited to kind of work on the whole stack. Of course, like not the whole stack, but that's why when we think about, do we want to be a software company or a hardware company or like the days of play, like it all ties in together. To do it really, really well, you have to have so Dan was describing our journey with MOSES, our journey with the electronic stack, and that's not even talking about all of the work that goes into setting up the software environment. But they all are so intricately related, and all of them come down to wanting to make the most usable product possible. Like getting these small MOSES is to make a consumer product. And so when we think about licensing, I mean, maybe, but the thing that gets us super, super excited is like, we're gonna have a product like this that's beautiful and easy to use, and anyone can have one. Anyone can use it.
Kid doesn't grow up saying like, I want to license something.
So I take it this base sits on something that goes
Yes,
through
yes.
six-
Yeah,
This
it's
is a-
rotational.
Yeah, here's
And is
one
that
of
a
the
motor
One
itself?
version.
no. That actually functions as a huge capstan as well.
Oh, so you,
What is the sort of your average power draw? Like if you were thinking in terms of some kind of mobile application for this, what kind of power draw would you have for your model there?
That's been that, but it's
Not necessarily peak, but on average.
I just to hold position, we're under an amp. I'm well under an amp when it's just lifting, and then it's going to scale directly with how fast and how strong you want it to be.
And this is at what, 12 volts, 24?
We are running at 24 volts right now.
24. And how scalable are your length dimensions on the arm? That looks kind of like I don't know, not a young child, but maybe a kid, 12 or something. If you were to go to slightly longer.
Well, and what's kind of
lengths.
interesting is we started with a much larger design.
Right, so
And
not
scale-
quite an industrial level where
Yeah.
it might be 6 feet across, but something that would be more like an adult arm, say, if you wanted to do a humanoid type applications.
Some of the arm we would. I guess it's kind of hard to answer that because every single parameter of the arm, like of our materials and our motor selection, has all been designed kind of for the size, and the size has been designed for the size of the motors that we can get, and for the magnetic flux that we can get out of neodymium before it hits. I think it's 160 before it demagnetizes. That's our
Curie point.
yeah. And that's we'll have a heat gun that's maybe we can get a bit more. And every single we came back from China with 2 bushels of carbon fiber, every single rod being different, trying to find, because carbon fiber is one. We were so happy because a lot of the materials it's much cheaper because of drones right now, and we can get straight carbon fiber rods, these are have final cosmetic roll wrap, but it's all unidirectional on the inside, and they are much cheaper because of drones. But the properties for any dimensions are going to change from factory to factory dramatically, and we have to test that because that determines our rigidity, which determines our modular elasticity, which determines what kind of accuracy we can actually get, and that factors into our controls. So we could definitely add or subtract some length to it, but if we were going beyond to a human scale thing, just for the balance of price and rigidity, I'd probably change the structure design at the very least. Joint design would stay the same, but the in between here would want a third strut and maybe a space frame, to have more working space frame for that kind of extension. But I'd have to run the FEA first.
Did you all get a chance to see what was used in the movie Gravity? How those cameras were? Who built those?
Those are KUKA robots. So KUKA that builds the big industrial. I mean, they painted them black and put button dolly on them, but they're KUKA robots. And actually, to use them, you need to know generally KUKA robotics language, which is ridiculous. It's ridiculous to have to learn a specific programming
Very
language.
unique, very one of a kind type of thing.
Yes.
Yeah, well, I mean, they're an old company, an old German company, and it made sense back then, but it doesn't anymore. We're in a very different world now. And so what Button Dolly did was that they wrote this Python script on top of it so that they could actually export the camera paths from Maya, so they'd have the virtual camera scene in Maya, and they're moving not just the cameras but the lights and the set, and they're moving everything in a very specific way to simulate zero gravity. And so they built the software layer on top of it. Now, which is really great, but of course you can't just go out and buy a KUKA robot. The arms are a minimum 100,000. The ones they use are actually more like $250,000 each. Yeah, but they're KUKA robots.
It's funny that at this moment you would come along and demonstrate this, because the Science Now program that's on PBS, they just did an article about the movie Gravity and how that revolutionary situation in photography.
Yeah, it's super cool. They showed, and they did exactly kind of that's what we're excited by, is when you take this, industrial automation and you put it into the hands of creative people who have, this vision of something artistic. And but none of them are roboticists, right? None of them will build the arm. But they essentially built an application for an existing arm, and then they were able to use it to do really cool effects. Now, if you want to do that as a photographer now, you can't buy the arm. You probably can't program with it. And there's you would, for Button Dolly, for instance, you buy the company to come and consult. Now they're bought by Google, so you can't even buy them at all. But they showed what can be done, and that's cool.
But at the same time, and there was a capacity mismatch, because the arms that
Yes.
KUKA was using, they changed photography, but for what they needed, you don't need to. These were industrial automation arms. These were meant for car assembly. You don't need to move a car. You just need to move a camera. And that's where it's kind of that similar ethos where we're trying to inject automation into areas that have not been automated before.
I noticed that Volkswagen over there, they're getting rid of their jointed arms because they're dangerous. They kill people.
Yeah.
They go get something wrong in their coat. And they don't want to have to make the factory so safe that it costs millions of dollars just to protect from this. So they're going about changing the entire arm assembly to something soft. And they went to the trunk of an elephant to study how it works, because it's very sensitive at the same time it's very strong. And they are developing robots to make the cars now. They're that way. There's 3 tubes that are concentric.
Yeah, the Festo arms, and
Those are pretty cool.
they are.
What are you intending on for the head? The user is supposed to be able to make some attachment to that, but they're going to have some interface up there that they go to. What are you envisioning as far as what the capabilities would be for that?
So we are at the base, at the very kind of easiest level of entry. we are developing a gripper that you can 3D print different attachments that will click onto it. So if you need to pick up a round object, which is kind of a pain for for a parallel gripper, you could, if you want to go crazy, you can use our scanner, scan the object, and have it automatically print a interface between the little gripper stubs and the object you want to grip, so that you can move it around. But we are also right now speccing out what the different kits will look like. So at the very minimum, we are making little flanges that you would need to connect onto this automatically. But then also motor drive boards, which are built in, and steppers and bearings and the other little kits and components that you can essentially take sort of a Lego-like approach to the construction of end effectors. But we are leaning very heavily on 3D printing because it allows people to fabricate new shapes. And in a lot of cases, what can be automated is, I can say maybe a third of like our quick use cases, we were able to just think something up and 3D print something that would hold a paste extruder for a cake, or hold a pen, or hold a laser cutter.
Now the vision is actually a part of the arm, and so you need to coordinate.
The vision system
something.
and the only vision system we have is in grippers that are actively using vision.
Okay.
So like the 3D scanner that we use has a depth camera inside that, and that has its own vision layer, and the vision is handled by a separate processor, but we don't have a camera built in right now.
But we have support for 3.
Yes, that's actually one of the really amazing things about working with Qualcomm is that they have really good vision libraries, and we're not using it yet. But we're making sure we break out all the pins that the processors we're using. Some of it's pre-released, so I can't talk about everything, but they can handle 3 simultaneous 4K streams of video and process that. And it's just like, so happy I don't have to do that.
You're using Snapdragon?
We are using Snapdragon.
Yeah.
Well, Snapdragons and Cortex M7s and a whole bunch of DSPs. Question?
Yeah, it's kind of related to the end effectors, but since you mentioned the idea of really supporting end effectors with cameras or vision capabilities, would you consider routing the communications cables all the way down?
Yes,
to the
yes. We are. Do you want to talk about that? Or?
No, it's good.
So we have a board on the inside that has a ton of pogo pins, which are like little spring-loaded contacts. And the idea is that we are routing all the communications you should ever need through the arm. Now that doesn't mean that each line is dedicated. Instead, we have a architecture on the bottom which lets you switch what those lines do. So we can only physically fit so many pins in there, but if you want 2 power and 1 speed and 1 UART, you can configure that, and it will change to the configuration you need. Or
Pretty excited about that.
yeah, or you can have the end effector itself request the pins it needs. So that's something we're working on, and it's kind of one of the next phase things. But we love our EEs. And
Can you say something about the joint sensors?
there is 14 bits of resolution in each joint.
They're like what, optical or
Magnetic,
magnetic? Okay.
absolute magnetic encoders. And they're very nice. I don't.
Is this anything you've had to develop, or you
We
off-the-shelf
work very
stuff?
closely with a German company, and it's actually we were using pre-release units for a long time, but I'm not sure how deeply I can go into like specific components before release. Yes.
You know I'm going to ask that question. So, can you talk a little bit about the capacitive skin, the sensing? It's pretty exciting.
Yeah, I guess I can now. The IPs. So one of the things we are super proud about is that we have developed a capacitive sensor which is built into the housing of the entire arm. So and this is so that we can do things like, so when we are using it, we were talking about how safety is like it's one of the number one things, but we didn't want to make the robot softer. We didn't want to make it, like less capable. Instead, by having the entire housing work as a capacitive sensor, it can detect collisions before they happen. Up to, we're getting close to 14 inches away, and we don't use that full range, but there is a tunable range where it will, if it's approaching a soft body, it will slow down and stop before it actually touches something. It also means that the entire housing can function as a touch-sensitive UI. So if you grip these things, it knows that it's in trainability mode, and it will react that way. If you grip it here, it knows that it should tune its like how much force feedback is going to each joint, so that it moves differently with that motion. We have a couple different ways we're doing that, but it largely works by using the plastic as a dielectric, and then pad printing nickel on the inside of the housing, a nickel paste, which we then flash, and then a dielectric goes over that, and then we sputter another metallized layer on the inside, which acts as a waveguide, and that directs the capacitive sensing outwards, and then we just use it like normal capacitive sensor. And we are playing around with a whole bunch of different patterns, because we can do really cool things where we change how sensitive different areas are, or like we make the wrist like a spin, like a wheel that can detect if you're like tracing around it rather than just proximity. But that is
feature.
Yeah, next version. First version that goes out to people, but
Yeah.
But
And I think that's really exciting and important because, like for instance, and I was sharing with you before, Rosanna, that we consider our robots collaborative robots. So we take a lot of sensor data. We fuse that just to understand the environment, and by you guys introducing this whole capacitive sensing capability, it just takes it to the next level. It's phenomenal because people and robots operate in the same spaces. Really, what we're driving towards, and that's why advances like these are just absolutely phenomenal and critical. Because nothing freaks out people more than a robot that doesn't really get them. Because we're used to operating with people near us, and if somebody doesn't respond to you, you just wonder like, what's wrong with the relationship? So, so with robots, I mean, and that breaks down that strange barrier that the uninitiated continue to erect. I mean, we've been pushing our robots into hospitality, for a good solid year plus, and it's amazing when you just talk to them, you show them a nice curved robot, no sharp edges, and some people are still kind of like, whoa, oh my god, and it's like, really? Sorry, I didn't mean to freak you out, because the robot's still just standing there, right? And they expect it to like kind of like sense them and turn around and look at them, but the fact that it didn't do that makes them think that okay, you really are a robot and you're weird, and the way to get that ubiquity is through more natural interaction.
Yeah, we were looking at a whole bunch of co-working environments and co-working strategies, and a lot of them kind of boil down to like when you bump a person, don't bump them too hard. But like at that point, you've already hit the person. And
That's a problem.
Yeah.
That's a problem.
Maybe you shouldn't hit the person.
So it's really, really cool because we can also like because we, in addition to just the sensor data, we also know where the arm is, and we know like past routines, and if it's if there is sensor data coming in that wasn't there before, like hey, it's a new object. If there is if we are approaching a soft body and we're getting higher readings from like the frontal sensors, like we know okay, that's us, that's not anyone else. If the relative increase in the in our our capacitive readings is higher than what we'd expect from our motion profile, we'll know they're moving towards us, and we can get these kind of sensor fusion insights, which are really fun. But it's something that we are really, really looking forward to, how we can make the UI more seamless and the user experience more natural. And that's a lot of what we feel needs to happen for robotics to be open, to be more approachable by everyone. Is that it's not this crazy machine; it's just in the tools.
So how much is it going to cost, and when is it going to be available for our Google freaks?
So we were looking at base model of probably around 2,000. Still, there's some things changing with our BOM, but that's sort of what we're going for. And then pre-order campaign next year, early next year.
So to 2016.
Yeah.
So
There's a mailing list somewhere.
There is a mailing list. Oh, yeah.
that's the MRSP?
Yeah.
So, okay, so you have to make it for $500.
I mean, thereabouts. It's the margins are a little bit different in when you do retail. You want that kind of 5x. We're not at the point of retail.
We're not selling these at Best Buy.
Right. No one like this. It doesn't make sense to buy at Best Buy for something that's a robot like this. A lot of the direct sales and selling through like Amazon is totally sufficient for us. We really want to make it as cheap as we possibly can, because the way that we get the real value is, yes, it's the mechanical stuff, and we're really proud of all the stuff that we've developed. But what we're really excited by is what people are actually going to do with these arms and how they're going to contribute to all the different applications. And a huge part of that is how cheap can we make it to really get it out to people. So that's why we're constantly thinking about how do we drive down cost. But that segues in. We're giving away 10 for free. So it ties in perfectly with we have this vision that just as there are mobile app developers, there will be robotic app developers, and there are very few people now who can sort of see beyond the horizon of how robots can be used. I mean, the question we get asked more than anything else is, what would I use it for? By certain people. Then there are other people who are like, just give it to me. I already know what I'm going to use it for. Like, I'm going to set it up in my workshop. I'm going to set it up for 3D printing. I want to put a camera on it. And there's this chasm, right? There's this chasm between the people who already have this creativity and they know what they want to do with it, and they know what like a tool like this is capable of, and the people who don't see it yet. And in order to kind of cross that chasm and get to some level of ubiquity, the people who can already see what's coming around the corner have to kind of help the rest of everyone else to see that. And so what we want is to find 10 developers who can help us show people what you can do with an arm. And that can be anything. It can be the workshop use cases. It can be like, oh, here it is just like helping sand. Here it is, 3D printing on a cake. That's the whole point of that is something that you wouldn't expect. And we don't necessarily care about decorating cakes, but some people really, really do. And it can be film case. It can be some of the interest we've had is in assistive devices, like people wanting to set them up for family members and people they care about who have difficulty just navigating their home. So what we're looking for is just, I think, 10 of the most eclectic, important use cases that we can think of, or not that we can think of, that people can think of, and people who are able to sort of build them, and then share with people what they've built. And our sense is that there is this sort of army of really cool developers who are going to help pave the way for this to become ubiquitous, and that's what we're looking for.
Some robbing ATM machines wouldn't probably.
No,
we
but
might
you
feature
could,
you on the awesome.
you could
Someone
displace a
will
lot
feature
of you could displace a lot of low paid jobs by say having it, I don't know, flip burgers.
Different company working on that right now.
Yes.
I have a question about your experience in Shenzhen.
Yes.
In particular, how much preparation or little preparation you had before going? You take just a plane, land, it's like, okay, knock on the door.
We had no preparation.
No preparation
Okay,
whatsoever.
and then since you said you were 6 months, what kind of budget, how much, because you were building it, so were you there actually at a workshop or something, or?
We just had a shared work environment.
Yeah, so you guys heard of Hackcelerator? Hacks now, I guess.
Yeah.
It's a program that takes you out to China, and it basically, you show up knowing nothing about hardware, and they help you with some of those contacts of, these are the electronics markets. These are how you negotiate in the electronics markets. They help you kind of go to factories and figure that out.
So you got introduced through them, so they were
Through them.
providing the
Yeah, you still have to.
background, the things.
They were, and so you have like an office. There's some food there. Someone's holding your hand for a couple of weeks, but a lot of it's figuring it out on your own, for sure.
And from a budget point of view, it's like did you had
How much we spent? I know we could eat for like $3 or $4 a day.
How'd you
The
afford
living
it?
expenses are very, very low.
How'd you
And-
afford
Yeah.
the airplane ticket to China?
There's actually a direct from San Francisco to Hong Kong, and then it's just Shenzhen's just on the border of Hong Kong, so it's not too bad. But in terms of development, our costs went way down, and that was actually a huge part of why we were able to redesign the robots so significantly. Like those three-phase motors, three-phase steppers that Dan was talking about, we were not able to afford them in the States, so they just bearings. There was this one bearing that we really wanted to use, and it was, I think, like $83 here. It was 73 cents in China.
Oh, wow.
So we got a pack of 10 or more.
There's a bearing in your keyring. Which is
Right.
we get a lot of bearings. Bearings.
So yeah, our development, we did stock up. We got a little excited. But yeah, so the cost of development went way down. With bearings, with motors, with carbon fiber, like Dan was saying. You have to test for quality, and it's still very difficult to find the parts that you need. So what we'll do is we'll find the parts in the States, like Consumi or like some DigiKey or catalog, and then the fun begins, because China is very cheap, but it's also pre-data sheet. So like everyone knows that going through data sheet sucks, but it's even worse if you do not have a data sheet. So there was a lot of just getting things ordered to the office and hooking them up and testing out what they actually were. Like,
Yeah.
and for the PMSMs that we found, I don't know that any of them said that they were PMSMs.
And we had to work with people to get them.
Yeah.
We had to, like, in a lot of cases, we would spam by like a whole bunch of things and then find out best quality ones, and then like meet with the factories. And
So there's a lot of groundwork. So you can get cost savings, but you have to be willing to be in the trenches to do that, or have somebody on your team who can do that.
that said, there are quite a few tours being run by I know Ian from Dangerous Prototypes runs one.
Yeah, Seed Studio.
Seed Studio runs one, and
Yeah.
they're these little like kind of like cruise packages like for Shenzhen, and they will take you around in a group, and you'll have a place to stay, you'll have a place to eat food, and they will kind of show you the ropes. But that's a would have been nice. Just moving there.
Do you have any qualms in terms of, I don't know, reliability? I mean, will the factories run like MTBF specs for you or something? I mean, how do you handle that?
It all depends, and it's all based on the personal relationship. And it's a very different culture there. If you have an adversarial relationship with a factory, things will slide.
Fun fact, the contract is the beginning of a relationship. So when you have whatever terms are in the contract, you can forget them. It doesn't mean anything if there's a contract. It just means like, I like you like me, let's start to do business.
But
It's a relationship.
but like if you have like babysit their kids, then they're not gonna like. It's all relationship based, and they can do just about anything you ask, and they can get any quality standards you ask if you're willing to pay for it. But that's a relationship that needs nurturing and a good deal of monitoring as well. And every single person I know that's in hardware production, for every production batch, they at least have one person on the floor. But when the cost savings are in order of magnitude, it's worth it.
You also, I would say, you have to be careful at every level of the supply chain, because there's the people that you work with. So, the easiest hands-free version is picking a CM, and they sort of source things for you and say, don't worry about it, we'll get everything, just like approve this. But they have suppliers who have suppliers who have suppliers. And we definitely found that there were a lot of materials that said they were one thing and were actually another. And it isn't necessarily the fault of the manufacturer that you're working with, but it doesn't matter if it messes up your product. So there's a ton of metal fraud. I think there's something like 70% is contaminated. No, not what it says it is.
Yeah, it's like the alloys are not quite there, and like, okay, we really need those alloys. And yeah, you the other big part of production is that you have to design everything for testability, and from your boards to every bit of hardware, and like you have to, if you like from day one design with testing in mind, you will save yourself so many headaches. And
that was the first advice we got from pretty much all our friends who were in hardware, was to design for testing. Did I mention design for testing?
Yeah, I can't wait for you guys to get together with other entrepreneurial people that are doing these new brilliant things like Stacks, their little company. Their whole gimmick is designed for testability, and all of their tests can be converted over to manufacturing. And they have a super smart way of going about this, but they don't know who to sell this brilliant stuff to. So they need to hook up with somebody like you, and then another one that does another thing that's very unique and modern, and it's gone away with all the old rules. That synergy is going to be awesome.
Yeah, there's definitely a lot of movement in that. Like a lot of people are trying to help aid in just making building easier.
What code do you use to make everything work?
It's almost all C.
Yeah.
C and C++, just for the speed that we have to run a lot of things at.
High
But-
level is Python. People
yes.
interact with Python.
Yes, like
or
the-
Arduino.
Yeah.
Which is sort of C++. Anyway.
Got to deal with memory management. So we do a lot of work behind the scenes to make it as stable as possible, to make sure that you can run Java on top of it, you can run Python on top of it, you can run Arduino-like languages on top of it. But back end, it's a mix of largely C, some Python. One guy tried Haskell.
Working
Some of
with
the
Chinese manufacturers, any concerns about IP?
Yeah, I mean, there are a few ways to sort of deal with that, and one of the things that we want to look into now that things are a little bit less crazy. I don't know why I said that. Things are not less crazy. I mean, it's just priced every day. They're not less crazy.
Slightly less crazy than last week.
Slightly less crazy, but is looking at doing some of our assembly in Tijuana, so you can do things like have sub-assemblies made at different places and then you bring them together. A lot of the defensibility, though, is not ever necessarily going to be in the hardware. It is in the platform, it is in the applications, the data set, and the community that you build. So yes, we can build in some fail-safes, but we also sort of don't kid ourselves that there won't be potential slip-ups with that. One of the best examples is when we were in China the first time. It was 2 months before the iPhone 6 and iPhone 6 Plus were even announced, and you could buy them on the streets of Shenzhen.
We all had iPhone 6s.
And we're like, oh, I wonder if that's actually how it'll be, and it was identical. It was an identical phone. So Apple can't do Apple can't do. But there are strategies that you can put in place. The bigger thing is that hardware itself is not sufficient.
And what can protect you somewhat is software's controls, is
Absolutely.
other things like that. And our controls are tough. But if the person who's burning our chips decides I'm gonna burn a lot more, then we better have a good relationship with that person or supply the chips.
Well, if you can reflash them, then you can just let them burn it with some minimal set of instructions for
A lot of
testing.
people do that. Yeah.
A lot.
And they have to.
A lot of different strategies around that.
Well, that's
Yeah.
the world of piracy, so you almost have to have some kind of strategy like that, because if they can copy it, they will.
You saw that question?
Yeah, speaking of software and it's getting into the hands of developers, do you, and I guess you mentioned focusing more on like the Arduino crowd, that sort of development level. Are you intending to just leverage as much as you can in terms of development environments that already exist for these sort of platforms, or do you plan to put in some effort to make even easier UIs to develop on graphical programming languages, that sort of thing?
I think where we are is sort of a combination of the two. We definitely think it's very important to go to where people already are. That's a big part of usability, is that we reduce the barrier to entry. At the same time, there are some specifics that you wouldn't necessarily have with Arduino that you do have with a robot, like having an in-browser simulator. And so I think it's really, we're looking at it as a combination.
Yeah, we have some. Can't talk about complete fact, but the next, it's not quite an IDE, but it's more like a composing robotic sequences like you would music is sort of the larger. But that is for we actually have another friend who's working on Scratch composition and some Treehouse stuff. and actually quite a few people who want to move to visual programming languages just because they're artists and they want artsy things. But we are, in addition to like trying to adopt languages people already know, we're trying to look at what are a newer, easier way to interact with robots, while also making sure that we, like, any raw data that you want to access, you can access. If you want to work with this thing in C, you want to get the the unprocessed, unfiltered data streams. There's some limits just due to bandwidth of like a network connection, but we try not to put any any restrictions in place if you want to go really low level.
So what is the interface then?
You mean like physically
How
programmed?
do you communicate with this?
Well, so it's running a Snapdragon, so you can like that's right now you SSH into it, but like there will be a drag and drop interface, or you will load applications onto it like you would a phone, and work on it on your desktop, and then right now it's ugly and a lot of command line stuff.
Question about the platform. So the iPhone, or to say the smartphone, the amazing thing is that it's a self-contained environment where you have much better sensor than what you need for the phone, and then people start using that for other applications. So here you have the gripper or whatever you're gonna the attachment that could be kind of something that kind of break a little bit the platform part that is providing flexibility, but then you need my little gripper, and that's an additional barrier. What's your thought on that?
Yeah, it's definitely a different beast. I mean, that's the iPhone is probably the best analog, but it will look different because there's different hardware. And so we have attachments that we're building, and so within that, we can guarantee that they work a certain way, and we can guarantee that when we release a library, it's as easy as if it just already came with your phone, and especially with the things we've done with just making the quick disconnect. It's like snap on, snap off. It's registering what, like, you don't have to individually program like, oh, I'm using this gripper, because it knows. And so it makes the platform a little bit. It becomes a background process, so it's not as obvious. But certainly there is, for when you're 3D printing your own gripper, it's going to be like there just is a hardware component to it. And it's
Looking at some like abstraction strategies,
Yeah.
how if you have something that has 2 joints and they're in a fixed position on an end effector, is there a easy way to abstract and describe a lot of different end effectors, and how can we build that into a pre-programmed chip on the end effector itself, so that the end effector the attachment can request the resources it needs, but also interface with software seamlessly, and that's hasn't really been done yet. So we are trying a couple different strategies, and that's one of the reasons we are releasing this to developers. Is based on what they develop, we're going to change a lot of stuff, and we want to see how people break this and what walls they run into.
So you're gonna put out a basic library that says wrist, turn left, right.
Yeah, there'll be a
that
bunch
sort
of
of
things.
thing. So you have a set of commands that you can immediately access. This.
Yes,
Yeah,
there'll be an
absolutely.
API, but
So each
sorry.
attachment,
Since we are running out of time, maybe we can have last questions, and then if Rosanna and Dan can stay around like a few more minutes, we can just open up to questions.
Sure.
so each attachment will have some ID chip so that the rest of the system knows what it is.
yes, we're working on A, a unique identifier, and B, a way to handshake and request the ports that you need. Basically. Yeah, I think that's the last question.
Okay. Cool.
Thank
Yeah,
you so
we'll be
much.
around. We'll be around for a few more minutes.
Do you want to do?
Did you guys want to see some of the demos?
Yeah.
Yes.
That'd be great. While Jen's setting up, so next week Dylan's gonna run the ROS workshop. I'm kind of excited about that. Also, Maker Faire, as you guys know, October 3rd and October 4th. Make sure to grab a ticket, and there's gonna be really fun
exhibitions there. I've been kind of checking all of those out. It's awesome. So you guys all should be there.
Yeah.
All right. Thanks.
I'll be home.
I apologize for the screen size. If you guys want to gather in a spot that's easier to see.
Okay. So this is the cake decorating where we have the iPad app, we sketch it on the iPad,
Yep.
and then let's go for music. And so we're handling the inverse kinematics, we're handling the G-code interpreting, and this actually, we just like printed this little end effector. We've got, that was one of the examples Dan was talking about with, where we've got a holder and then we just put in an extruder.
Another one to see.
Oh, the laser, show them the laser. Okay, that's really cool.
It's cool because it's laser.
Yeah. We did not break anything.
So these end attachments, are you going to license that, or is that going to be some open source?
We're hoping to open source.
We want it
these
to be
as
open
well.
as possible.
Okay.
Yeah.
It's unnecessarily loud.
Yeah. Really.
This is a laser cutter then?
Yeah.
Probably won't sell that one.
Yeah, we're not selling it. I don't think that. Like, I don't even think this is a legal laser here. We got it in China. They shouldn't have sold it to us. I don't know. Like,
It's also, there are legalities also to putting flamethrowers on it, we found, especially in California.
It's just indoors.
So those are two of our demo videos. So yeah.
What was that
Yeah.
cutting?
I'm sorry?
Fabric? The laser?
What was the piece that we had that we were cutting?
Plywood?
Oh yeah, it was
Balsa
balsa wood.
Balsa wood.
Balsa wood, yeah.
And a desk, and also can give a desk.
Yeah. Good part of a Qualcomm
So
workbench.
there we go.
Whoops.
Wait, Piggy's still there.
Oh.
Never mind, Pig. We didn't cut through a workbench.
We didn't do anything.
Oh, yes, right. Yeah, we are absolutely trying to.
Did you host the DEF CON, it's not paranoia, they're really coming after you one?
Oh, no, that wasn't me. But I'm there. Yeah. But, you know, this is the first year we missed it in a very, very long time. Because our company is just not in the year. And at that time, it was just too good.
I just realized I should tell people. Is anybody interested in signing up to apply for a free robot? Okay, I'm sorry?
We've hit it up already.
Oh, you have? Okay, excellent. Cool. Alright, and you've gotten the emails and everything?
We have, yeah.
Did you make the submission yet?
No, I was thinking about it. I was thinking about it.
Okay.
We actually have a very cool diagram already.
Okay.
It's funny because we have an application. Then I saw you guys and I was like, this is perfect. So I'm gonna send the diagram.
Cool. Well, I can actually post. I think I'll post on the meetup. And I posted on the Facebook. I'll link to it so that everyone gets it because it's easier to do that from your own computer. I don't know. It's kind of silly. So.
I haven't even gotten close on
Oh, you got it. You got it. That's fantastic.
Right. Right. Great. And then you're building